Let's discuss question number 48 and 49. This is a common data question from test 1. Okay, and this is basically from vibrations, so theory of machines. Okay, so now what is asked? So basically from vibration, and I can just write it as vibration as well. Okay, so a structure is given. We have a spring on one side which is K1, the spring, and a mass hanging M, K2. This is A, total length is L. This is A, this is P. Okay, and what we are asked to find the deflection at point P in case of static equilibrium. So now we'll go step by step. Now AB is assumed to be rigid, so AB doesn't deflect on its own. Okay, so only expansion what can happen is in springs. Okay, so for the first bit we are asked to find the deflection in, or the how much point B has deflected. Now because of this weight, the point, there will be a downward force on point B, but then when this point B tries to move downwards, there will be a force that is, this spring will try to expand and thereby creating a upward force which will try to balance the rod. So this upward force, because of this mg, the point B tries to move down, so there is a force, downward force mg, that is acting at point B. Okay, so let me just draw the free body diagram at P. So at M you have mg, and this is your expansion which is K2 delta 2. Let's say the spring has expanded by delta 2, K2 delta 2. Now in case of static equilibrium, so my mg has to be K2 delta 2. So in turn here you have K2 delta 2 or mg, whatever both are same. So this is at point P. Now this expands by some amount, so I can, so this is just a free body diagram. Say the force that comes from the spring is F1, and at this point you have all the reaction force. Okay, now one thing I want to make, that this has to be as this has to be, this should be able to freely rotate about this point. Okay, so instead of, because what I feel is it shouldn't be a fixed, because if it is fixed then this can't rotate, it's a rigid, it can't rotate, so there has to be kind of a, don't think that it's a fixed joint, it is a something kind of a hinge joint. Okay, so I have F1 here, F2 here, and these reactions S, R, A are there. Now I need to basically find out the deflection of NP. Okay, now because of this F1, now this has gone like this. Ideally this would go like this, so there will be some deflection delta B, and this is the deflection in spring 1, this is delta 1. Okay, so this is how the structure would look like. This is your free body diagram, and this is how the deflection will look like. Okay, so now taking this free body diagram, balancing moment about A, we get mg into L, producing clockwise moment, that should be balanced by this moment produced by F. So minus F1 into A, this is 0. Now mg into L is F1A. F1A is the spring force in K1, and so F1A can be written as K1 delta 1 into A. So delta 1 is mg by K1 into L by A is the deflection in the spring 1. So this is my deflection in the spring 1. This is A, the total is L. So I can basically apply, this angle is constant. Remember that what is given in the problem is wrong. This shouldn't be a fixed, there is a hinge here. So applying similar triangles here, what I can get is, or tan theta from this equation, the above curve geometry is tan theta. If I consider only this triangle, because this is straight. Okay, so I can consider this triangle tan theta is delta 1 by a, and I can consider this big triangle where it is deflection of b by total length L. Now I want deflection of b delta b, which is delta 1 into L by a. Delta 1 I got from the moment balance, which is mg by k1 into L by a, and you have L by a, so it is mg by k1 into L by a whole square. So the answer is B. The option is B here. Sorry, option is C here, because mg L square by k1 square. Okay, in B you don't have a square. So this is the answer. Option is C. Okay, this is for 48th bit. Now 49th bit, we are supposed to find out the frequency vibration of the system M. Now for this, there is one thing which I need to tell you. Say if you have only a spring and M, okay, so we can write at the static equilibrium that mg is k delta. Okay, and so in this form, g by delta, I have k by m, where k is my stiffness, spring stiffness, and this is my mass, and this in fact is my omega square, or the square of the natural frequencies. So if I can bring anything in this form, so this will be my equivalent stiffness and this will be my mass, and I can just get from the omega square. I can basically, once I get the equivalent stiffness, the root of equivalent stiffness by m would be my natural frequency. So the basic idea is get the total deflection of the mass at static equilibrium. At static equilibrium. Okay, so now this mass mg, the deflection of the mass will be the deflection of the point B plus how much the spring K2 has expanded. So expanded of the spring, second spring. So delta B we already got, which is mg by K1 into L by A whole square. The spring will expand of the amount delta 2, which is mg by K2. So this I can write mg by K2. So this together will become mg L square by A square K1 plus 1 by K2. This is your delta M. So again, writing in this form, okay, I need to get omega, which is equivalent K by M. So I need to write this in terms of G by delta M. So G by delta M would be 1 by of this, that is, okay, so let me just write in another page. G by delta is 1 by M and 1 by this entire thing. So this will be your K2. Okay, let me write down in another page. Let me turn the page. So this is what we got. So let me write what we got from the before. We got that delta M is mg into your into L square by A square K1 plus 1 by K2. This is what we got. Now we need to just find out the equivalent stiffness. So let's multiply L square by A square into K2 plus K1 by your K1 K2. Let's take the LCM. It's delta M. So we have to all express in this form. Mg is K equivalent into delta. This is what we need to express. So this, let's take the entire thing to the side. So K1 K2 by L square by A square K2 plus K1 is your equivalent stiffness, delta M is mg. So this is my equivalent stiffness comparing with the static equilibrium for only a spring and a mass. So this is my equivalent stiffness, and so my Sutler frequency is equivalent stiffness by mass, which is my K1 K2 K1 K2 by Okay, so let me just put this here. K1 K2 by L square by A square K2 plus K1. Okay, my mass. And my frequency is 2 pi by omega, or basically, I mean, how is my omega defined? Omega is basically my circular frequency, and so omega, basically this is the way, I mean, omega circular frequency is related to the linear frequency in this way. So omega is 1 by 2 pi, frequency, linear frequency is 1 by 2 pi omega, which is 1 by 2 pi root k1 k2 by your mass into L square by A square k2 plus k1. Let's see whether we have anything now. K2, okay, so A square by L square they have written, so one of the option matches this, but slightly k1 by k2 they have written is, so A square by L square, let's multiply A square by L square. So basically I am multiplying and the numerator and denominator by A square by L square. So this is what I get. In the numerator, when I multiply by A square by L square, I get the term A square by L square. Denominator, when I multiply A square by L square, for K2 will become free. K1 you have A square by L square. So this is how you find out the natural frequency. So remember that the general procedure, one of the easy procedure, instead of writing everything in a dynamic and then finding out all that, best is write the force balance equation in static equilibrium. The equation, express the equation in this form: mg is equal to k equivalent delta. We need to find k equivalent, and then the natural frequency expression is this. So the option for this is A for the 49th bit, for 48th bit it was C. So it all comes from the deflection. Write down the static equilibrium. I mean, at the point of static equilibrium, write down the force balance equation. That is it.